This year we're going to be studying things that are very, very small and very, very large. We're going to start the year by studying physics at the quantum level, and in April and May we're going to wrap up by studying things at the astronomical level. So to kind of introduce us to that, let's talk a little bit about ranges of magnitude and these quantities in the universe. This is IB topic 1.1. When we talk about orders of magnitude, we're talking about 10 to the power of something. 10 to the first, 10 to the second, 10 to the third. And hopefully we are comfortable at this point with our orders of magnitude. So if we say something is 10 to the 0 power, what is that? That means it's equal to 1, right? Okay? If we have something, for instance, let's say we have something 3 times 10 to the 5th. Okay, it doesn't matter what the particular measurement is. That number, this is our scientific notation, is equal to 3, 1, 2, 3, 4, 5. And the chicken scratch is I'm going to have to deal with it this year. So 3.0 times 10 to the 5th is the same as 300,000. A lot of times we estimate orders of magnitude, or we talk about things just in terms of their orders of magnitude, and if we were doing that, we would say that this measurement was of the order of magnitude of 10 to the 5th. Particularly when we get to things that are very, very large or very, very small, the difference between 1 times 10 to the 205th is not very significant if you are comparing it to 3 times 10 to the 205th. The difference there is not a whole lot, and so we can just talk about things in their orders of magnitude. If we look at some things in the universe, the mass of the universe is about 10 to the 50th kilograms. If we kind of look at everything that's in the universe, bring all that mass together, down to the mass of an electron, which is 10 to the negative 30th. So that's a difference in order of magnitudes of 80. So that's pretty significant, and we're actually going to be looking at all of those different levels this year. You can see some other interesting ones here as well. The length of time it takes light to cross a nucleus is about 10 to the negative 23 seconds, so that's very, very small. We also are going to be comparing ratios of orders of nuclei, or orders of magnitude rather, excuse me, and it's just like any other ratio. Here we're comparing the ratio of the diameter of a hydrogen atom to the hydrogen nucleus, and so the hydrogen atom itself is much larger because it includes both the nucleus and that electron that's orbiting around the outside, and so the diameter of the hydrogen atom is roughly 10 to the 5th, 10 to the negative 10th rather. The hydrogen nucleus, on the other hand, is on the order of 10 to the negative 15th. So again, it's just math. 10 to the negative 10 divided by 10 to the negative 15th is 10 to the 5th. And so what that tells us is that the hydrogen atom itself is 10 to the 5th times larger than just the nucleus. Now, along with this idea of orders of magnitude, just something that's kind of cool, and you can look this up on your own. It's just scaleoftheuniverse.com, all one word, no www. And all it is, it's a short interactive flash program that compares things in the universe. At the significantly smaller end, we have what's called the Planck length, which is about 10 to the negative 35th meters, and the idea is that you can't really have anything smaller than that. And that's roughly what we call points, and then if we look at how small this is, we're measuring here in yoctometers. Yoctometers are essentially our smallest prefix, our smallest metric prefix for measurement, and we have 0.00000000001 yoctometers. Now, if we start to really get into the bigger areas, we're going through all these. Finally, we get to 1 full yoctometer. And 1 yoctometer is 10 to the negative 24th meters, so decimal, 23 zeros, 1. That's roughly the diameter of a neutrino, and we'll talk about those in a couple weeks. As we get larger and larger, we start to get to some of our subatomic particles, and maybe the first thing that you've heard of before, the quarks. Quarks have an average diameter roughly 1 atometer, which is 10 to the negative 18th meters. And so these are our constituent particles of protons and neutrons. It's also roughly the size of our electron. Then we have femtometers. We're starting to maybe get to sizes that you've heard of. Average size of an atom's nucleus is about 10 femtometers. Then we're getting larger. Picometers, 10 to the negative 12th. Now we're into the range of electromagnetic radiation, some of the highest energy electromagnetic radiation, which is our gamma radiation. As we get larger, we're getting into atom sizes, molecules, nanotubes, and then here we have DNA. DNA's thickness about 3 nanometers. And we're going to keep getting bigger and bigger and bigger till we get to pollen. Now we're getting to things that we can start to see unaided with the eye. Ants, quail eggs. There we go, quail eggs. 1 square inch is 2.54 centimeters, so 2.5 centimeters on a side. There's your coffee beans. These are important. You should know everything you can about coffee beans. They are significant. Humans, okay, about 2 meters, give or take. And so here we're kind of in the range of our everyday, 10 to the 0 to 10 to the second, maybe, depending on what we're looking at. You have something like the Eiffel Tower, which is pretty tall. Angel Falls in South America, 10 to the second. And then there's Sears Tower. Okay. Now we start to move on a little bit faster, and we get to some of our non-planetary, so to speak, objects. Mercury. Here's our moon up here on the upper left, about 3.5 megameters. Our moon, you can see, is bigger than Pluto. It's about the same diameter as the U.S. is across, a little bit smaller. And some of the other moons from other planets. Then we get to the actual planets and the sun. Now, if you look closely, you can maybe see the dot that is Earth. There it is. And by the time we get to a magnitude that's the sun, our Earth is not quite so significant, but then we're coming out to some real stars, and all of a sudden our sun becomes pretty insignificant as well, and our sun is actually not much more than a medium-sized star. And so we're getting out here to some pretty significant distances. Petameters, 10 to the 15th. The Oort cloud is where all of the material for our solar system came from. Then we get into some of our further away nebulas, and all our globular clusters, which again we'll talk about at the end of the year. And keep going. And we have the Milky Way galaxy, which is 120,000 light years. And going. Here's the edge of the observable universe. You can't see further than that because the light hasn't gotten to us, and it won't for a while because the universe isn't old enough. And here is the estimated, and that's an important term here, estimated size of the universe. Again, we'll talk about astrophysics content at the end of the year. Next, we will talk about measurement.